another really key lemma, which is called approximation. And this is now an easy consequence of the previous complicated lemma. So what does the approximation tell us? That's kind of related to kind of how this integral is computed. Because nobody can compute in practice any supremums of all Borel functions or stuff of that sort. So to prove to calculate anything, we need to kind of way to approximate these integrals, and this is an approximation thing. So the approximation says, let's pick any positive measurable function f, and let's pick any simple functions which are finite range measurable and positive, such that these simple functions approximate f from below. Then what we claim is that this complicated looking integral of f can be calculated as the limit when n goes to infinity of these simple integrals fn d mu. This is a practical way of calculating the integral. But to make sure that it's true, so let's make a proof of this using the previous consistency lemma. What is the proof is that let's see, the monotonicity of simple things implies that these integrals are ordered, these simple integrals. Again, these are ordered because the functions were ordered and we proved the monotonicity. So they are ordered, and that's why the limit exists and is well defined as an extended real number. This exists as a number in between 0 and infinity, including infinity. What else? We know that each of these are also less than, if we now recall that we had this extension property, so we can replace these squares by pluses. And we have also proved the property that these pluses were monotone. That's why, and all of these were less than f, so then we know that these are all less than f of the new plus integral. So we also know that this limit, which we know that it exists, of these simple integrals of fn's can be at most this integral of the plus integral that we know how to define. This is again kind of the first part that we prove this inequality. The other inequality looks harder, and it is harder, but that's why we kind of did this lemma that we have here. So for the other direction, let's say this is part 1. Let's do part 2 and try to reverse this one. So now again, we fix any g which is simple and dominated by f. Then actually what we did about the consistency lemma, what does it imply? It actually does imply that precisely what we wanted. In the consistency lemma, we prove that this limit fn is at least the integral of the g integral. Right? And now what? This is true for all g in df. Now let's take this fixing away because we no more fix anything. We just know that the consistency lemma implies that this is true for every G in the DF set. And so let's take the supremum of these. It follows that this limit is also at least the supremum. It must be at least the supremum of these G in DF on simple integral of G. And this is, by definition, this supremum is the plus integral of F. Here we have the other inequality direction. That's the end of the proof. And we are done actually with this approximation lemma. Again, time for questions. So far, we didn't have any single question. Should I interpret it so that you kind of follow or you kind of not follow? Or kind of everything is so clear that you don't need to ask, or everything is so unclear that you don't know what to ask? Show me green light if you think that this is more or less clear and easy to understand. Let's see how many green lights I will get. I will get a couple. Okay.
I can say that at least on my part, it seems clear. The only thing I was wondering that when we proved the equality of the simple integral and then the plus integral, why wouldn't the new integral inherit all of the properties of the simple integral?
It kind of inherits them in the special case that for the simple arguments, it does inherit them, but for the general arguments,
Yeah.
it does not automatically inherit.
Okay.
Yeah, it's a good point. In a way, we prove that it also inherits the monotonicity rather easily to general class of functions. And actually, that's what we have left. So finally, or maybe I would like to comment that what's the intuition about this approximation? This is actually very important lemma, so that's why we used so much time. So we have been using a lot of our common time to understand this in really high detail. So why did we use so much time? Let me try to maybe comment a bit on this. We ignore this proof. And in practice now, let's do a little example. So a little example. Think about S being let's say, the interval from 1 to 0, and calligraphic S then is the Borel sigma algebra on this 0-1 interval. And let's look at the function. So let's look at the function f, for example, looking like this. To bring and the space S is there, and then this is the positive real numbers. And now think about mu being the Lebesgue measure. According to lecture notes, it's denoted by lambda. So this is now the Lebesgue measure on this unit interval. And we want to calculate what's the Lebesgue integral. So we want to calculate, let's say, this is our function f here. We want to calculate the integral. What's the integral of f? Assume it's measurable, so then we should be able to do what's the Lebesgue integral of this f here. So how do we compute this? By the approximation lemma, we need to find simple function that approximate f from below. So what do? We use this approximation that we divide this part of the space into tiny intervals, and then we say that we take the approximation from below. So we take fn to be the function that kind of stepwise approximate f from below. Here it's kind of flat, so it's constant on that set. And then we say that this approximation is Fn. N is now measuring the mesh size here. When n grows, so then this mesh gets denser and denser here, and then Fn will approximate F. In this setting, if you do this, so Fn will approximate F from below in the correct way. Fn only takes finitely many values because all values of Fn are in this lattice here that we fixed. So in this case, Fn happens to be simple and non-negative and measurable, and it's below F, so the conditions of the approximation are valid. Then we calculate the Lebesgue integral for each Fn. So then we know that yes, the Lebesgue integral of F for this such a function is the limit when we take the mesh size to 0 or n to infinity of this simple integral of Fn. And now the Lebesgue integral of this. And we know that this is the same as we look at the sum I from 1 to m, which now depends on n, because for every n we have a different function, and then we have here the value of Fn. AI, which also now depends on n, and then this Lebesgue measure. So now it's the length of the interval if these happen to be intervals. So we take the lengths of the intervals. So these are the pre-images now for this Fn function. So one pre-image is here. This would be one AI here. So we take the Lebesgue measure of AI, and that's the length of this, and then we take the value here. That's the value AI. So AI times the length is then the area of this box or this rectangle here. And so for some other I, so then we take this length, the Lebesgue measure is the length, and then we take this. So you see that this starts to look like an ordinary integral in the Lebesgue setting, although everything was so far quite abstract. Again, the distinction to make is that for standard Riemann integration, we are splitting actually, for Riemann integrals, we would be splitting this part of the space into tiny mesh. And we would approximate F from using these mesh points, and interpolate F. But that causes some problems when F is not the continuous function. So for let's say for polynomials, for trigonometric functions, they are continuous functions, so you can play with Riemann integrals and work with them there. For discontinuous functions, especially in stochastics, if you think of stochastic processes, which are quite often discontinuous, so then integrals are needed to be taking this mesh here.